Hello, my name is Daniel Runcie, and I'm an assistant professor in the Department of Plant Sciences at UC Davis. Today, I'm going to talk about our tool called MegaLMM, which we published in Genome Biology last summer. MegaLMM is a statistical model for genomic prediction with high-dimensional traits. Genomic prediction is a tool that's used today in plant and animal breeding programs to accelerate the rate of progress in developing new varieties. Plant breeding is not a new technology, and it's been tremendously successful at improving our crops. This graph shows grain yield per acre for corn in the US over the last 150 years, going from about 30 bushels to acre to nearly 180, a six-fold increase. Now, not all of this is due to breeding. There are also improvements in management that go along with this improvement in varieties. But this shows that potential is there with breeding to make transformative changes to our foods. However, an important point here is that while these changes are dramatic, they are not fast. It's been a gradual change of a few percent per year over the last 50 years or so. So breeding is effective, but slow. Why is it so slow? Well, the process of breeding is largely a filter for very rare events. The general strategy is to start with generating a large pool of candidates and then going through a sequential rounds of testing, each time selecting the best lines while generating more and more evidence on which few lines are the best. Each step here generally takes a year or more, especially as you get down towards the bottom, where the best candidates will need to be tested in many trials in many regions over many years. Genomic prediction is a tool for speeding up this process. If we can use genomic data to predict which of these large numbers of candidate lines are the best, we can skip some of these steps of growing and phenotyping plants and move faster through this sieve. This technique has been revolutionary in breeding programs in recent years. My interest, though, is how we can use other types of data beyond genomic data to supplement this genomic prediction and make breeding more efficient. For example, say that we want to predict grain yield of different wheat lines. Can we use drones or other things like that to collect, say, hyperspectral data to make these predictions more accurate? Reflectance data provides information on how plants are actually growing in the field, things like their vigor, nitrogen allocations, disease preferences, and such. Can we use these types of data to reduce expensive yield measurements or potentially grow more lines if we can only measure them by drones? For example, if reflectance data and grain yield were correlated like this, rather than measuring grain yield directly, we could predict it based on these other traits. This would be efficient if the reflectance data or other secondary trait data were cheaper to measure, faster to measure, or could be measured earlier in development than the target trait itself. However, the problem with this is that this correlation that we see here may be due to non-genetic variation, say something like a water gradient across the field, where we have patches in the field that get a lot of water and say patches that get less water and more stressed. If so, this correlation may not be telling us anything about which lines have the best genetics. In order to figure this out, we have to decompose these correlations between the correlations due to genetics and the correlations due to the environment. The standard approach for this is using what's called the multivariate linear mix model. Using these models, we can estimate these correlations, which we call the matrices G and P. Usually this is done with frequentist or Bayesian methods. The problem with this is that that the size of these matrices increases quadratically with a number of traits. For example, if we have 600 traits, each matrix would have about 300,000 parameters we have to estimate. This makes estimating these matrices extremely computationally intensive and statistically fragile. So the solution that we've been working on is a new way to parameterize and fit these multivariate linear mix models that scales very well to high-dimensional traits. We're calling this method MegaLMM, and we've developed an R package for it. I'm not going to go into how MegaLMM works today, but this graph shows that MegaLMM scales much better than any other similar package I'm aware of. On the x-axis here, we have the number of traits per line in a data set. and on the y-axis, the number of hours it took for that model to converge. MegaLMM is approximately linear scaling for up to 20,000 traits, while the other models scale quadratically or cubically, and so take many hours for many fewer numbers of traits, and become not practical at all for larger data sets. However, the speed of MegaLMM in large data sets doesn't impact its accuracy. So what I'm showing here is the prediction accuracy as we add random subsets of additional traits. And there's no sign for MegaLMM that it's overfitting when you give it larger and larger parameter spaces. So how well does it work in actual breeding scenario? To test, I used, a cross-validation scheme where I masked half of the yield measurements on half of the lines, and then used the other lines, the rest of the data on all the lines to predict these held out values. To start, I compared 3 flavors of genomic prediction, which just uses genetic data, and we get prediction accuracies about 0.4 or 5. When we add the hyperspectral data in, we can do quite a bit better. But the difference between the blue bars and the red bars is that in the blue bars, these methods don't make any attempt to separate genetic and non-genetic correlations, and so they overfit the correlations, leading to poorer out-of-sample performance. But MegaLMM, which can separate these correlations, does much better, leading to an almost doubling of prediction accuracy, meaning it could roughly double the rate of gain in these breeding programs. So to summarize, I've shown that breeding is necessary for transformative changes in our crops, though it is a very slow process, but careful and comprehensive use of all data can accelerate the process, rate of progress. And we think that MegaLMM should be a useful tool for helping to incorporate new types of data into breeding programs. And with that, I'd like to acknowledge people in my lab and collaborators, funding sources, and encourage you to use our R package, which is available on GitHub.